Thank you, Nigel. I'm told this is a very diverse audience. I'd like to see how diverse, just to get a handle on what levels I should span. So let me just ask, how many of you are physicists, astronomers, or mathematicians, sort of at the graduate student level or higher? Okay, that's the bulk. So how many of you are not in the sciences at all? Okay, good. I'm going to talk to you. But I also talk to those who are professionals. I thought it was really appropriate, given Andrew's great abilities at communicating science and enthusiasm for science. I thought it was appropriate to talk at a level that is aimed in large measure at people who are non-scientists, but with a fair amount of sprinkling of things that for the scientists themselves. So let me begin with an epoch 1.3 billion years ago, when here on Earth, multicell life was just spreading over the globe, but in a galaxy far, far away. Two black holes circled around and around each other, and here you see from a computer simulation what they would have looked like to your eyes if you had been there. There's a star field, a rather uniform star field back behind them, but you see patterns of, in that star field which are caused by what is called gravitational lensing, where the light rays come from a star, travel through the gravitational field, the warped space-time of a black hole, in some cases go around the black holes a few times and then come to your eyes. And that bending of the light rays causes the patterns that we see. The two black holes orbited around and around each other, creating ripples in the shape of space and time called gravitational waves. And those ripples, as they traveled out, they carried away energy, enabling these black holes, or forcing these black holes to spiral closer and closer together. And as they neared each other, the warping of space and time became enormous. They collided and emerged together in a gigantic cataclysm that gave off 3 solar masses worth of gravitational wave energy. It was as though you had taken 3 suns and annihilated them and turned it into pure energy of gravitational waves. And those waves came off so fast, that 3 solar masses worth of energy, so fast in a fraction of a second, that the total power output, the energy that was coming off in a unit time during the merger, during those roughly a tenth of a second, the total power that came off was 50 times larger than the total power output of all the stars in the universe put together. So 50 universe luminosities during a very brief period of time, carrying off a total energy of 3 solar masses. Those waves traveled outward, away from the galaxy in which the black holes lived, into the great reaches of intergalactic space, across intergalactic space, and they arrived at the outer edges of our own galaxy, our Milky Way galaxy, 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. They traveled through our galaxy 50,000 years. They arrived first at Earth at the Antarctic Peninsula, traveled upward through the Earth, emerged from the Earth at Livingston, Louisiana, where one of the LIGO gravitational wave detectors is, emerged at Hanford, Washington, where the other one is, 7 milliseconds later, 7 1,000ths of a second later. And they created a signal in those gravitational wave detectors that I'll talk about in a few moments, that the LIGO team, the LIGO collaboration together with colleagues from the Virgo gravity wave detector program here in Europe, the LIGO and Virgo collaboration, 1,000 people stared at the data, poked and prodded the instruments, trying to be absolutely sure this was the real thing for 5 months. And at the end of the 5 months, announced to the world the first detection of gravitational waves. I've shown you some of the people at Caltech, MIT, Hanford, and Louisiana, Livingston, Louisiana, and the GEO collaboration, Glasgow, Cardiff, Hanover, who played a very major role in this. The group in Glasgow was responsible for very advanced suspension systems in the LIGO detectors. The group at Hanover was responsible for the laser and a lot of the important optics. And the group in Cardiff was responsible for a lot of the data analysis. So a very major contribution from the UK and from Germany, and also from a number of other countries. A total of, within the LIGO collaboration itself, 16 nations, something like 80 different institutions, and 1,000 people. When the results were announced on February 10, the newspapers in February 11, I think it was, it hit the front pages of newspapers all over the world, from India to New York City, London, Bakersfield, California, just a number of unbelievable places as well. And it was really sort of a phenomenon, a cultural phenomenon. So how did we get here? I'm going to tell you the story in brief from my personal point of view and then move onward and talk about the future. So this begins with Albert Einstein in 1916. He had just formulated his general theory of relativity in 1915, and about 6 months later, he predicted the existence of gravitational waves, and he told us that the gravitational waves stretch and squeeze space, stretching in one direction, squeezing in the opposite direction, and then an oscillatory stretching and squeezing. What that means operationally is if you have two inertial reference frames, one here and one there, and anything that is sitting at rest initially in that inertial reference frame remains at rest, the inertial reference frames move back and forth relative to each other. And so anything that is remaining inertial, they move back and forth relative to each other. And that is the meaning then of the stretching and squeezing of space. That is one aspect of a gravitational wave. If there's time, I'll talk a little bit about other aspects. In his classic paper in 1916, Einstein said, in effect, these waves are so weak from any kind of a conceivable astrophysical source that humans will never see them. But in the 1960s, Joseph Weber at the University of Maryland recognized that technology had changed enormously, and that the possible sources of gravitational waves had changed enormously. So one now had lasers and computers, and technologically the concept of a black hole and a neutron star, which would be far better sources of gravitational waves than anything that had been conceived of in Einstein's era. These were well established. And so Weber said, gee, maybe we can do it. And he was the first person to have the guts, the chutzpah, to build a gravitational wave detector. He did not, in the end, succeed in detecting gravitational waves. But he inspired me, he inspired Ray Weiss, he inspired a number of people who went on to push forward on the LIGO project. In 1966, I moved to Caltech from being a graduate student at Princeton and built a theory group then focusing on black holes, neutron stars, and gravitational waves. I began to think about the issue of what could you do with gravitational waves if you had a gravitational wave detector. And it seemed to me that was particularly important was the contrast between gravitational waves and electromagnetic waves that are normally used by astronomers to study the universe. Electromagnetic waves are oscillations of the electric and magnetic field that propagate through space-time, whereas gravitational waves are oscillations in the fabric or the shape of space itself. Electromagnetic waves, astrophysically, are almost always incoherent superpositions of emission from individual particles, atoms, and molecules, whereas gravitational waves are the coherent emission by the bulk motion of mass and energy. This shouldn't really say matter, because black holes don't involve matter, but they have mass, so they have energy. Electromagnetic waves are easily absorbed and scattered, all too easily, by intervening dust. And gravitational waves are never significantly absorbed or scattered, even near the Big Bang. And so the contrast is enormous, and as a result of that contrast, it seemed to me and my colleagues, such as Stephen Hawking and Gary Gibbons, who were also thinking about these things in that era, that many gravitational wave sources would not be seen electromagnetically, and indeed the colliding black holes that LIGO discovered have not been seen electromagnetically. And there would be huge surprises, since our current knowledge of the universe based on electromagnetic waves that are so different from gravitational waves. The electromagnetic waves are seeing aspects of the universe that are by and large quite different from what gravitational waves will see. And so extrapolating from our electromagnetic observations does not give you a very good, we expect, a very good handle on the most exciting things that may be seen gravitationally. Ray Weiss was a postdoc at Princeton when I was a graduate student. We knew each other. We both, he was a member of Bob Dickey's experimental gravity group. I was a hanger-on in Bob Dickey's group as a theorist, but very eagerly attended the meetings of Bob's research group every week and listened to Ray and the other experimenters talk about gravity experiments. I was doing theory with John Wheeler. Ray went back to MIT at the same time as I went to Caltech on the faculty. And Ray began thinking about gravitational wave detectors. And it took a while to gestate. But in 1972, he wrote a paper, a technical paper, that is really the most brilliant technical paper that I have ever read. In this paper, he described a new type of gravity wave detector that he had conceived, but had been conceived independently by several other people. But what he did that nobody else did was he went in, and with this gravity wave detector, he identified all the major noise sources that such a detector would face. Well, in fact, that the first version of LIGO, the first LIGO detectors would ultimately face, and described ways to deal with each of those noise sources, and estimated then what sensitivity could be achieved, and concluded that if you made these detectors long, sizes of a few kilometers, that they had a reasonable possibility to detect the gravitational waves that I and other theorists were predicting might exist. But the remarkable thing about this is that Ray didn't believe you should publish this kind of stuff until you had actually detected gravitational waves. And so he put this in an internal MIT technical report, which, however, he did distribute to colleagues. And and of course, he changed his view on whether you publish or not within a few years. But that was his view at the time. The idea that Ray had was you would take a laser beam, you would send it through a beam splitter, and you would have here two mirrors hanging from overhead support. So we're looking down on these mirrors. And two mirrors there hanging from overhead supports. A distance separation here of a few kilometers. And the laser beam, when the gravitational wave came along, it would push these two mirrors apart, push those together, and the next time cycle push these apart, push those together. Laser beam would come in, it would go through a little hole in these mirrors, bounce back and forth many times to build up a signal, and then come back, recombine with the light from that arm, recombine at the beam splitter with some of the light coming out toward a photodetector here. The key point was that as these mirrors moved apart and those mirrors moved together, the round-trip travel distance that they would be had in the two arms would be measurably different. You would measure the difference by the interference of the two beams here, standard optical interferometry, and you would see the strength of the light, the intensity of the light coming out toward the photodetector rise and fall as the mirrors moved back and forth, riding on the stretching and squeezing space. I looked at this. I had not yet studied his paper, but I heard the idea that he had. And I was in the midst of co-authoring a book called Gravitation with Charles Mizner and my PhD advisor, John Wheeler. And I just looked at it, I looked at the numbers, and it was obvious that this was not a very good idea. And so we were about to go to press, and I wrote in there, and you can go in and read it, that this is not a very promising approach. And of course, then I wound up spending 60, 70% of the rest of my career trying to help the experimenters make it happen. Why did I think it was not promising? You just look at some numbers. How big was the motion of the mirrors back and forth relative to each other? You begin with 1 centimeter, divide by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that is being used to make these measurements. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100 again, you get the magnitude of the motions, the largest motions that we might expect to see if the separation between the mirrors is a few kilometers. And it's obviously not very promising. Except if you were a good enough experimenter, you had a big enough team, you had enough resources, I became convinced it could be pulled off. I became convinced by studying Ray's paper, by talking in depth with Ray and with Vladimir Braginsky, a superb experimental physicist who also began working in this field actually before Ray did, but working with other types of ideas for gravity wave detectors already in the 1960s in parallel with Joe Weber. And so I became convinced and decided that I would like myself to do whatever I could to help the experimenters pull this off, and that I would like to then build a research group at Caltech to collaborate with Ray Weiss and others on making this happen. The key person that I helped recruit to Caltech to do this was Ron Drever, who was at the Glasgow University. Ron, in the mid-1970s, several years after Ray's work, had several key ideas for significant improvements on Ray's design. One of the first was to operate each arm of these interferometers as a Fabry-Perot cavity. For those physicists who are in the audience, what you know is that this means that the light comes in, it goes through the glass of this mirror. There's a highly reflecting coating on the inside. A little bit of it leaks in, but then it gets trapped in here and builds up to very high intensity between the beams, between the two mirrors, and then it leaks back out. And so it's basically Ray Weiss's design, but with all of those individual beams bouncing back and forth between the mirrors, overlapping each other. And this was harder to do, which is why Ray was not at all enthusiastic about doing it. But in fact, if you could pull it off, and Ron was convinced you could, it would be more versatile and simpler. And that's how it did turn out to be. So in 76 to 78, we made a decision to create our experimental group at Caltech. We recruited Ron from Glasgow. We recruited Stan Whitcomb from Chicago. He was working in infrared astronomy at Chicago, had just recently gotten his PhD. And the two of them led Caltech in building a 40-meter interferometer as a prototype, 1% of the ultimate length of the LIGO interferometers. In parallel, at MIT, Ray was completing a much shorter prototype interferometer and beginning to work with it to prove out some of the techniques. But he was, more importantly, had fielded a feasibility study for kilometer scale interferometers. What were all the things that could go wrong? What did you have to deal with in order to build them? And this dealt with not just with conceptually, but with the construction costs, the practical things, the steel that you would have to deal with and, for large vacuum pipes, the outgassing of hydrogen from the steel, which would cause us noise when the laser beam goes through a tiny bit of hydrogen that's leaked out of the vacuum tubes into the interior. And the laser beam is slightly perturbed. All kinds of practical issues such as this. In 1984, well, I guess it was late 83, we came together, Ray's group and our group, presented to the National Science Foundation, to the physics division, the results of his study of the feasibility and the issues you have to deal with in building big interferometers. The results of the interferometer prototypes at Caltech, at MIT, and also in Glasgow, and a group led by Hans Billings that was at the Max Planck Institute just outside Munich. And we came together and convinced NSF that they should fund us to start working toward this. And so we got off and running with NSF support and a project that was overseen by Weiss, Drever, and me. These were two experimenters who didn't always see eye to eye. Those of you who have read Jan Levin's book about this know that's a slight exaggeration. They rarely saw eye to eye. and I was the peacemaking theorist. Troika was a phrase, a Russian phrase, that in that era tended to mean a very dysfunctional leadership, and we were as dysfunctional as you have ever imagined. And so we led this in a dysfunctional way for 3 years. And then we were told in no uncertain terms by NSF and by the leadership of Caltech and MIT, you get yourself a single director who has the authority to make final decisions. It will not be somebody who's already working in the field, because there's nobody already working in the field who has those skills. You bring somebody in from the outside who can quickly learn the key science issues and has skill and experience at making technical decisions and organizing a project of the sort that you're trying to do. And so we did that. We brought in Robbie Vogt. He had been the first chief scientist at the Jet Propulsion Laboratory and had been the provost at Caltech and had done large space experiments. He led us both in merging the experimental efforts at Caltech and MIT, which were headed in sort of rather different directions, forced the two teams to work together. He led us in writing the construction proposal for LIGO. Construction proposal and said we would build facilities at 2 different sites to hold these interferometers, vacuum systems and so forth. And then we would build inside and operate inside these facilities 2 generations of interferometers, initial interferometers at a sensitivity that would give us real experience at working with these very complex instruments, and would have a possibility of seeing gravitational waves, but probably wouldn't see anything. And then advanced interferometers, once the team had experience with the initial interferometers, saw where the problems were, and then did the final design of the advanced interferometers and the final technology development. Advanced interferometers at a sensitivity where we should have a high probability of seeing a lot of gravitational waves. And so that was the strategy. We struggled for 2 years to get funded. There's a cultural difference between physics, or at least there was in that era, physics and astronomy. Astronomers, many eminent astronomers, could not really imagine that it was a reasonable thing to do to build 2 generations, where the first generation costs $300 million, and then the next generation is going to cost you something comparable. To build 2 generations of instruments before you see anything. Whereas physicists who are accustomed to staging things like this. And so we were coming out of the physics community. We had our funding from the physics community. And as a result of that, despite some opposition from eminent astronomers, we did manage to get funded. Congress gave us our first funding toward construction in 1992. And the US Congress has backed us with enthusiasm ever since, regardless of who is in power, the Republicans or the Democrats, which I have to say I'm very impressed by them, because they were funding us at what now comes to a total of $1.1 billion over all of these years to look for gravitational waves that nobody had ever seen, although there was some strong indirect evidence for its existence in observations of binary pulsars, for which Hulse and Taylor got a Nobel Prize. And we were developing technology to make those exquisitely tight measurements that I talked about that seemed almost crazy that you might be able to do it. But they bought into it and backed us to the hilt. Barry Barish took over as director. He had more experience in actually running big projects and was much more skilled at the management of big projects than Robbie Vogt. He took over in 1994, and 94 to 99 we built the facilities. 97 Barry began the process of expanding LIGO from a 2-institution project to Caltech and MIT to what now is, as I said, 1,000 people in 80 institutions in 16 nations, the so-called LIGO scientific collaboration, and expanding into Europe and Asia. So it's a worldwide collaboration now. And he led us in the construction of the initial interferometers and in the earliest searches with the initial interferometers. Then, because he really, I think, is widely regarded as the most skilled organizer and manager of very big science projects, he was stolen away from us by the high-energy physicists to lead the design of the Great International Linear Collider, the next large accelerator that the high energy physics community has been thinking about building. And so we had then a succession of two other directors, Jay Marks and David Wrightsey, who have led us to where we are today. The completion of the searches of the initial interferometers, the installation of the advanced interferometers 2010 to 2015, and the first detection under the leadership of David Wrightsey. And I can't emphasize strongly enough the necessity of a very effective leader of this sort who is given the power to make decisions and who has the wisdom to know how to get all the information from colleagues that are necessary to make decisions and to try to foster joint decisions but make a firm decision in the end if everybody doesn't agree. In the meantime, before I come to the first detection, I want to talk about what was going on the theory front. Vladimir Brzezinski was both a theorist and a great experimenter. He warned us already in 1968 that no matter how we went about attempting to detect gravitational waves, we would ultimately have to face up to the issue that we would be monitoring the motion of very big masses with such exquisite precision that we would see them behave quantum mechanically instead of classically. We would see the quantum mechanical fluctuations in their positions. And we would have to deal with those quantum fluctuations in their positions and make sure that they did not get in the way of detecting the gravitational waves. More precisely, we would have to, in the case of LIGO, if that is the direction one went, which we did, one would monitor motions of 40-kilogram mirrors to a precision that is approximately the half-width of the wave function of the center of mass degree of freedom in the mirrors. And that is what is done in advanced LIGO, or when advanced LIGO reaches its design sensitivity. One must deal with the Heisenberg uncertainty principle then in terms of its influence on the motion of the mirrors and circumvent it so that these fluctuations in position don't get in the way of detecting the gravitational waves. For the first time, humans see human-sized objects behave quantum mechanically. And so Brzezinski group and my group got together and pushed very hard through the 1980s and 90s and into the 2000s to develop what Brzezinski called quantum non-demolition technology to deal with this. Technology for getting a gravity wave signal through these fluctuating mirrors without demolishing the signal. And so that is a major piece of the future of LIGO. We don't need this technology today because we're not yet at design sensitivity. We need the beginnings of it in 2020 when we will be at design sensitivity, and we need it in spades as we move on beyond that. Also on the theory front, it was clear to some of us already back in the early 1980s that we would have to have computer simulations of LIGO's gravitational wave sources, or at least of some of them, probably of most of them, in order to be able to understand what it was that was coming out of the gravity wave detectors. Because the gravity wave detectors measure the pattern of stretching and squeezing, sort of like the pattern of a sound wave that you put on an oscilloscope, that you stretch slowly, then suddenly squeeze fast, then stretch and squeeze at various speeds. And it was those waveforms that carry the information about what's going on in the source, and you would have to have computer simulations of the sources to produce waveforms to compare with the observed waveforms in order to know what's going on. So there was a big effort to develop these technology for these simulations that began at about the same time as the experimenters started working on LIGO, or started working on gravitational wave detection at all. It began in the 1960s. I was the chair of the advisory committee to the International World Consortium of people who were doing these simulations through the 1990s, and I saw uphand at their meetings twice a year how badly things were going. And so in the early 2000s, I stepped out of being involved in LIGO on a day-to-day basis in order to start a research group of my own at Caltech working in computer simulations, hand in hand with what I thought was the strongest other group in the world working on this, which was a group led by Saul Tukulski at Cornell. And the thing that we were doing differently than others was we were convinced that to pull this off successfully, you had to have something bigger than 2 or 3 professors and a handful of students. So we built a group of about 30 people, so an intermediate scale, sort of between tiny science and LIGO science, to do these simulations and pushed them on through called the SXS project, Simulating Extreme Space-Times. I have to emphasize that just as I didn't build the LIGO detectors, I also didn't write the computer code for this. I am more of an enthusiast. My role has been much more of knowing what needed to be done, knowing the science that we were going after, and helping the people who were doing the numerical relativity and the experiment make decisions about what do they do in order to meet the things that were needed in order to have success. So my role was never a real hands-on role. September 14, 2015, the computer simulations were well in hand. By that time, not only our group, but several other groups who were capable of doing it as well by then. The first search for gravitational waves with the advanced LIGO detectors was scheduled to begin about 3 days later. The instruments were being brought into their final state, tuned up to begin that search. And as they were being tuned up to begin that search, a gravity wave signal came in. The experimental team froze the parameters of the detectors and said, this is the configuration of the detectors we're going to use for our first search, a search that would go on for about 4 months thereafter. But it was quite remarkable. The signal came in just before the configuration was frozen. This was what the signal looked like coming in from Livingston, Louisiana, and it was so strong you could see it by eye. All that has been done here is to remove the part of the signal below 30 hertz and the piece above 300 hertz. So it's bandpass filtered with 30 hertz to 300 hertz, just the way it came in, raw signal. And then it's tapered off a little gradually below 30 hertz and above 300 hertz. And we never expected that the first signal would be something you could see by eye. We thought we were going to have to pull it out of the data in the data analysis. Same signal from Hanford, Washington. They matched perfectly within the noise. Cleaned up the signals and wound up with a gray signal. And the red is from the numerical relativity simulations by our SXS team. Comparing then that, and so you had to compare with a huge number of different waveforms, all for black hole collisions that had different masses and different spins on the black holes. And by identifying which set of parameters for the masses and the spins of the black holes matched the best, it was concluded then by the LIGO team that we were dealing with a system that was made of 2 initial black holes with masses of 29 solar masses, 36 solar masses. That's a total of 65. Final black hole, 62 solar masses, spinning at 67% of the maximum possible spin at a distance of 1.3 billion light years. Now, I have not told you the spins of the initial black holes. They are not well measured. They're quite uncertain to a fair extent because we're seeing this system roughly face on. And the way in which the spins of the black holes influence the shapes of the waves is each black hole drags space into motion. We call it dragging of inertial frames, which then motion of the space causes the orbit to precess. And if you see the orbit edge on, the precession is quite obvious in the wave shapes. But if you see it roughly face on, you don't see much precession. And so we have not been lucky yet. We haven't seen as yet any black hole merger that is roughly edge on, but we surely will. I mean, nature was kind enough to give us a big signal, not kind enough yet to give us one seen edge on. So we don't have good spin measurements on these. The measurement of the spin of the final black hole comes, and the mass and spin of the final black hole measured come from looking at the ring down, the frequency of the oscillations as the final black hole is pulsating, and the rate at which it dies out. But in fact, in this case, we did not get a very good measurement of that ring down. this 67% of the maximum spin really comes from the computer simulations that tell us that. It's not a measured value. And I will return to this when I talk about attempting to test Stephen Hawking's area theorem in a few minutes. We carried out the O1 search, our first gravity wave search, from September 2015 to January 2016. We saw 2.8 black hole mergers. 2 absolutely firm black hole mergers at the quote 5 sigma level, probability that they're not real, statistically a part in 100,000. And 1 where we have 80% confidence that it's real. But that's high enough that we pay some attention to that in doing statistics at this early stage on black hole binaries. So these are the 3 signals that we're seeing. The second and third ones had lower masses. This was 3 billion light years away. The others were about 1.3 and 1.4 billion light years away. An 14 solar mass and an 8 solar mass black hole here, 23 and 13 solar masses. So we're beginning to get statistical information of black hole mergers. Now, let me just give you a visual impression of just 3 pictures of LIGO. LIGO is in Hanford, Washington, is seen from the air. The arms of LIGO, you also saw that, a variant of that at the beginning of my talk. These are vacuum system from which the mirrors hang in here. A mirror hangs in there. There's a beam splitter in this chamber. Barry Barish, who made this slide for us, he put a baseball player in here so you get a sense of the size of this vacuum system in the corner of LIGO. This is a mirror, one of the advanced LIGO mirrors that's hanging, weighs 40 kilograms. It's roughly the size that you see it there. It's sort of like this, 40-kilogram mirror. It is hanging freely, though it has a lot of housing around it to protect it, and as part of the system for being able to control the mirror, keep it always pointing toward the other mirror, so light will bounce back and forth between the mirrors. So, in other words, so each arm remains locked as a Fabry-Perot cavity. There are 100,000 data channels at each of the 2 LIGO sites. And that's a measure of the complexity of these instruments. Those deal with both the monitoring of what's going on internally in each of these instruments, but also monitoring the environment. So that when you see something, you really know what's going on with the instrument, you really know what's going on in the environment, and you can diagnose whether it's really a believable thing or not. This means that these instruments are very complex, and each of them has its own personality, though the personalities are quite similar, but they're not perfectly the same between the 2 instruments. So it is like, I've forgotten who it was that designed Frankenstein, but had to learn Frankenstein's personality after Frankenstein came to life. You have these 2 instruments, very complex. The experimenters had to poke and prod to learn their personalities and figure out why they are not at design sensitivity. Why are they 3 times worse than design sensitivity? They're designed to see 3 times farther than they're seeing, and they're not. And so that is a process then we went through with the initial interferometers, and it takes a handful of years to do. And so the first step in that, February to November of last year, the experimenters poked and prodded, learning the personality and figuring out some of the things that are not quite right in there. They're a little different, enough different from the design that they need to be fixed. And begin the first stages of coaxing these instruments toward their design sensitivity. But the decision was then made to go back and search again without very much improvement, during which time the experimenters then plotted out step by step what would they do to deal with the things they'd learned about the instruments. And so the second search, the so-called O2 search, is now underway. And sometime during the O2 search, we hope, near the end of the O2 search, because it's getting toward the end, the advanced Virgo detector near Pisa, Italy, which has been designed and built by a consortium of Italian, Dutch, French, and some Polish physicists involved. There may be some others as well. We hope that it will join the search. The Virgo scientists participated in the analysis of the LIGO data for the first detections. From the beginning, there has basically been an agreement between them that we share data completely, we analyze data completely together. And so we would hope that we have another detector operating, and I'll explain why that's important in a few minutes. So looking toward the future, by 2019 to 2020, we expect advanced LIGO to be at design sensitivity. By then, we're seeing 3 times farther into the universe. So we are seeing a volume of the universe 3 cubed, or approximately 30 times bigger. Since we're seeing roughly 1 every other month at the present time, we should be at that time seeing a few a week instead of 1 every other month, maybe even 1 a day. We're dealing with statistics of very small numbers thus far, 2.8 discovery detections as yet. Oh, I should say the first results from the O2 search will be published within the next month. And so you can watch for the very first results from the beginning of the O2 search. And the O2 search will continue on toward the end of the summer, and then the team will go back to poking and prodding and improving, and ultimately reach design sensitivity. We expect 2019, 2020. Black hole emerges a few per week, but many other sources, other types of sources seen. We think it's likely we will see gravitational waves from pulsars, spinning neutron stars, gravitational waves from black holes tearing apart companion neutron stars, gravitational waves from colliding neutron stars and neutron star binaries, if we're very, very lucky. But these things are few and far between. At the distance that LIGO can see, gravitational waves from the core of a supernova explosion. I'm not going to go into the details of this, but many of you are familiar with these kinds of sources. And these 3, we have a very good shot at seeing all of these at design sensitivity, but we have to be quite lucky to see supernovae because of their rarity. And then at some point there will be some giant surprises, but I can't tell you when, and I can't tell you what. For binary black holes, no electromagnetic signal has been seen. But for the other sources I talked about, there will surely be electromagnetic signals, and with some neutrino signals. We call this multi-messenger astronomy, gravitational waves plus gamma rays, X-rays, light, radio waves, neutrinos. And so there is a collaboration between the LIGO team and electromagnetic astronomers around the world and neutrino astronomers, working together to try to get any non-gravitational wave signal that may accompany the gravitational waves, and then use the combination of all these data to figure out more in greater detail what's going on. This multi-messenger astronomy has, however, a very big problem. This shows you the location on the sky, the error box. I've forgotten what it is. It's something like maybe a 2 sigma error. The location of the first gravitational wave signal that came in. What I'm doing is I'm plotting this on the surface of the Earth, and all this means is that the signal came in most likely overhead at the Antarctic Peninsula. And with a reasonable probability that it was actually overhead somewhere near the tip of South America and so forth. So this is an error box for the first signal, which was very strong. The other 2 were much weaker, and these are the error boxes. The orange is the error box for the other very high confidence detection. There are 2 regions that it might be in, and then this is the 80% probable detection, very uncertain. It's not, it would be much better for the electromagnetic astronomers if we could tell them more accurately where this signal is coming from on the sky, obviously. And so the key to that is a network of gravity wave detectors, because the primary way in which we determine the direction of the source is by the time delay in the arrival of the signal at various locations on Earth. So as I mentioned, Virgo in Pisa, Italy is likely to go online sometime later this year. In addition, we are preparing for installation of a LIGO detector that's sitting where all the components are sitting in boxes at the moment, to be installed in India. And The Japanese have a detector called Kagra that is being installed inside the mountain where the Kamiokande neutrino detector resides. With these additional gravity wave detectors, we can localize the source much better. If I just take LIGO plus Virgo, then we've already got it down much better than what I showed you for the LIGO alone, for the 2 LIGO detectors. We still have long error boxes like this. These are just error boxes. If the source happened to be here, then that's the error box you would have. And if you bring in LIGO India, suddenly these error boxes get much, much shorter in the north-south direction. You bring in Kagra, and they get shorter in the east-west direction, but they're already pretty darn short in the east-west direction. But this international network is really pretty crucial for pinning down the locations of the sources that are seen. Beyond advanced LIGO, there is a firm plan now for the next stage, which is an improvement on advanced LIGO called LIGO A+, which I'll give you a measure of how much improvement. Instead of seeing a few binary black holes a week, it would likely see something like 5 a day in the 2023 time frame, roughly. 2028 would be see the turn on possibly of something called LIGO Voyager. I won't describe what this is except to say it is an improved gravity wave detector in the existing vacuum systems. And this is about the earliest that the team could mount that and start beating down its noise. And so observations at this level of several per hour, binary black holes per hour, and then, of course, many, many other kinds of sources, beginning sometime soon after turn on in 2028. Sometime in the 2030s, something called Cosmic Explorer, an Einstein telescope with much, much longer arms. Cosmic Explorer, the vision is 40-kilometer arms, and capable of seeing every black hole merger in the universe with masses below about 1,000 solar masses. So I won't go into the details, but you can read the details of these things. Just look up their names on the web. So this is the fastest things could develop. It depends on money coming together and no big unexpected technical surprises. We actually expect to have 4 gravitational wave windows onto the universe within the next 2 decades. By a window, I mean a frequency band in the gravity wave spectrum. So I would speak about the radio window that's explored with radio waves electromagnetically, the X-ray window explored with X-ray telescopes. So 4 analogs of X-ray, radio wave, optical astronomy. LIGO looks for gravitational waves with periods in the millisecond band, actually 10 hertz. So 100 milliseconds up to about 1 millisecond, roughly. There is something called LISA, which is 3 spacecraft that track each other with laser beams that is likely to be launched, if all goes well, roughly 2030 is now what the European Space Agency is talking about, with looking for gravitational waves with periods of minutes to hours. Something called pulsar timing arrays, where radio astronomers look and monitor the ticking rates of pulsars, a number of different very quiet pulsars with very regular ticking rates at different locations on the sky. Very roughly speaking, though this is a cheat, as the gravitational wave sweeps across the Earth, it speeds up and slows down the clocks on the Earth, making it look like all of these pulsars are slowing down and speeding up synchronously. But it's a little more complicated than that. That's for gravitational waves with periods of years to decades. And then gravitational waves with periods of hundreds of millions to billions of years through the cosmic polarization of the cosmic microwave background, which many of you know about, but I'm not going to go into here. But it's yet another technique looking for gravitational waves with very, very much longer wavelengths, longer periods. And so this is a field that is just going to burgeon, we expect, and I think we can be fairly confident that all of these are going to succeed, as I say, within roughly the next 20 years. So I want to say a little bit about exploring black holes with gravitational waves. Because Stephen Hawking and I and a few other people in the audience participated in the golden age of black hole theory research of the 1960s and 70s, in which a number of very interesting things were discovered theoretically about black holes. And the key thing is that we expect with LIGO and its international partners to be able to explore these phenomena observationally. Black hole uniqueness, so-called no-hair theorem, that says that if you know, for astrophysical black holes, if you know the mass of a black hole and its spin, you know all of its properties. So these black holes are relatively simple in that sense. Theorem due to the combined efforts of a large number of people, Israel, Hawking, Carter, Robinson, all of the key initial contributors basically being here in the vicinity of Cambridge. Well, I guess Israel was in Canada at the time. Bunting and Mazur as well, coming along in the 1980s to clean up some aspects of it. Black hole pulsations throw off the excess hair. By the excess hair, I mean all the properties of the black hole that are not what they should be for a black hole with a given mass and spin. They've got to be gotten rid of. So if the black hole is deformed, the deformations have to be thrown off, and they're carried off by gravitational waves. Waves are produced by pulsations of the black holes, and this was all worked out in the 1970s, beginning of the 1960s. Stephen Hawking's area law, or the second law of black hole mechanics, and other laws of black hole mechanics. I'm going to talk about that briefly in a minute. As Stephen and Jim Hartle pointed out, that if you have two black holes going around each other, they will each raise a tide on each other, just like the tide that the moon raises on the Earth. And as they go around each other, the tide will move relative to the surface of the black hole, in a sense, relative to the horizon generators, for those who know about such things. And that there is basically a tidal friction in a black hole, a friction-like behavior that will cause then a change in the masses of the black holes and a change in their spins. It's a weak effect, but it is an effect that I'm quite sure Lisa will see and be able to test the details of what Hawking and Hartle predicted. And what people had not really appreciated until we had the computer simulations exploring the nonlinear dynamics of curved space-time. I'm going to talk briefly about three of these pieces of black hole physics that we expect to study with gravitational waves. Beginning with black hole uniqueness. Black holes, of course, are actually not made from matter. They're made from warped or curved space-time. The matter that was in the star that imploded to form the black hole has long since disappeared into the interior and been destroyed or transmuted, transmogrified, whatever word you want, by the singularity at its center. And so we can visualize the curved space-time of a black hole, which is determined just by its mass and its spin, according to these uniqueness theorems. In this way, you imagine that you take an equatorial slice through a black hole and you embed it in that's a two-dimensional surface, you embed it in a three-dimensional space, a flat three-dimensional space, and see how it has to curve down in order to be so embedded. But I prefer to describe it in the language of the movie Interstellar that I had a bit of a role in, is you're looking in from the fifth dimension. But for those of you who aren't familiar with the fifth dimension of Interstellar, you're artificially embedding this in a higher dimension. And so the shape of space looks like that. The color coding shows the slowing of time, 10% of the maximum time flowing at 10% of the rate far away, where you have the yellow, so right in here. Time slowed to a halt. This is really the lapse function in the space-time metric, in the Kerr space-time metric. And then the shift function, showing the dragging of inertial frames or the dragging of space into motion with angular velocity proportional to the length of those arrows. And so this is actually, for the equatorial plane of a black hole, the uniqueness theorem's prediction as to the precise shape of space and time, all aspects of the warped space-time in the equatorial plane. Now, Lisa with its spacecraft tracking each other with laser beams, will be able to study gigantic black holes that weigh millions of times what the sun weighs. And so if you have a small black hole, say 10 solar masses, going around a black hole of, say, 10 million solar masses, the small black hole goes along an orbit that I'm going to show you here, removing the warping of space here. But I'm going to show you what the orbit looks like, and it's quite impressive. This is from a computer simulation. So the orbit is dragged by the whirling motion of space, or the dragging of inertial frames. It is dragged into a form that is wildly different from a Keplerian orbit. And that small black hole basically samples all the space around the big black hole as it goes around and around the big black hole. Lisa's team has been developing the data analysis for doing this, for extracting the signal from something like that, a signal that would be built up over a period of a year or two with a huge number of orbits around there. And it turns out that the gravity wave signal from that motion carries a full map of the space-time geometry of the big black hole that's being explored by the little black hole as the little black hole goes around it. And we expect Lisa to be able to make exquisitely accurate maps of the space-time geometry and see whether it is the space-time geometry predicted by the black hole uniqueness theorem. So this, for me, is quantitatively one of the most exciting things. And what if this central body is not a black hole? Well, there's something called naked singularities that Stephen Hawking absolutely does not believe in. We've had a bet about this with Stephen, John Prescott and I for some time. Stephen is probably right. They probably don't exist. But you can write down a space-time metric for one, and this is the orbital motion of some stars around that central singularity. And when the star is close enough, the orbit is chaotic. Chaotic in the standard mathematical sense of extreme sensitivity to initial conditions. And the gravitational waveform is obviously extremely different from what you would have for black holes, a small black hole going around a big black hole. So a widely different map. Let me talk quickly about Stephen's area theorem, which of course says if you have two black holes that go around each other and merge, this black hole has a spin whose rate of spin is proportional to the length of the arrow, and the spin axis is along that arrow. And this one similarly. Black hole 1, black hole 2, they orbit around each other. Because of the dragging of inertial frames, the waveforms are quite interesting. There are two waveforms, it turns out, two polarizations, both of which the international network will get. So you get out two waveforms, just as you get out two polarizations or two waveforms for an electromagnetic wave. And you wind up in the end with a final black hole. And Stephen's prediction is that the sum of the area of the horizon of this black hole and the area of the horizon of that black hole will be less than the area of the final black hole. Now, for each black hole, we cannot measure the area directly. What we can measure is the mass and the spin. And we get the masses and the spins from the details of these waveforms. I won't go into it, except I already told you that to get the spins, you really need to be able to see these things edge on to get the spins of the two initial black holes. To get the spin of the final black hole, you have to see, and its mass, you have to see the ring down and measure the rate to which the final waves from the final pulsations of the final black hole die out, and the frequencies of pulsations of the final black hole. So there are ways, pretty straightforward ways in principle, to get the masses and the spins. And the area of each one is just Newton's gravitational constant, the speed of light, in this formula, and the masses and the spin angular momenta of those holes. So there's a formula that comes from the Kerr metric related to the black hole uniqueness theorems. And so you go in, you measure the masses and the spins of each of these black holes, and then compute the areas as A3 bigger than A1 plus A2. But you have to be lucky. You have to see the orbit roughly edge on. You best have at least one of those black holes spinning quite rapidly in order to get strong precession. And you need to have the final black hole be in the right mass range that you have a really strong signal for the final ring down in order to be able to see that final ring down. We have not been that lucky yet. I have not attempted to do estimates of how often we might be that lucky, but I'm sure it's at the level that I would expect we will likely have this by the time we reach design sensitivity. We will have a few examples. This is my rough gut guess without having done any real analysis. But I don't think we're likely to have this in the first two searches. Okay. So nonlinear dynamics of curved space-time, we now have numerical relativity simulations that enable you to watch the collisions of black holes by making movies based on the numerical relativity simulations. These are an embedding diagram, or as seen from the fifth dimension, of the collision of the first two black holes that were seen by LIGO. The waveform that we saw off of that first detection, all of the waves that were seen came off during the merger, during that final merger. So they contained entirely signal about the nonlinear dynamics of curved space-time for the first time. So now we have simulations, we have observations, the waveforms agree to high accuracy, and we're beginning as a team, the LIGO team, and the numerical relativists, to really pin down through observations and through the simulations what goes on in nonlinear dynamics of curved space-time. I'm going to skip this and just wind up with a few remarks about exploring the birth of the universe with gravitational waves. Of course, as you look out into the universe with electromagnetic waves, you only can see out to when the universe was about 380,000 years old. To astronomical accuracy, that's 100,000 years here. Earlier than that, the universe was so hot and so dense that the electromagnetic waves couldn't propagate. They were trapped. They were scattered. They were absorbed, re-emitted, and scattered. And so we get beautiful, in the cosmic microwave background, beautiful images of the universe at age 380,000 years, but nothing earlier. With neutrinos, we would similarly be able to see, once, if they are ever seen from the Big Bang, we would see what the universe looked like at 1 second age. Gravitational waves are the only form of radiation that's so penetrating that it could be produced in the Big Bang explosion itself, the so-called Planck era, and travel unscathed or almost unscathed by the absorption, re-emission, scattering by matter in the intervening period. Though whatever came off of the Big Bang well, let me return to that. So gravitational waves are the key tool for exploring what went on in the first 1 second of the life of the universe then. And I think that by the middle of this century, this is going to be the major thrust in this field, or at least one of the major thrusts, is exploring the first 1 second of the life of the universe. Primordial gravitational waves from the Big Bang, even if it was only vacuum fluctuations of the gravitational field came off the Big Bang, they are predicted to have been amplified to form a fairly rich background of gravitational waves that would have interacted with the hot plasma when the universe was 380,000 years old to produce a polarization pattern on the cosmic microwave background that we see today. And so many of you are familiar with this. Those of you who haven't understood a word I said. But just to say that this is one of the ways of exploring that first 1 second is through this cosmic microwave background polarization. My favorite is the birth of the fundamental forces. At age 10 to the minus 12 seconds, 1/trillionth of a second, theory predicts that there was a phase transition in which the electroweak force came apart, giving birth to the electromagnetic force and the weak nuclear force. And so the laws of physics changed. And that may have occurred, we don't know for sure at all, but that may have occurred as a first-order phase transition in bubbles quite analogous to droplets of water forming out of water vapor. And those bubbles then are predicted to have expanded basically at the speed of light, to have collided, and in their collisions to have produced gravitational waves. And in the intervening epoch between 1/trillionth of a second after the birth of the universe and today, they are predicted that the wavelength of those gravitational waves expanded until it is in the LISA frequency band. And so one of the goals of LISA is to search for stochastic background of gravitational waves from collisions of bubbles in which the electromagnetic force has been given birth. LIGO could see similar phase transitions when the universe was 10 to the minus 22 seconds old. We have no idea what was going on when the universe was 22 seconds old. But there are also things called cosmic strings that LIGO is looking for gravitational waves from, a well-predicted waveform. I'm just going to skip over this. Many of you are familiar with this. A very, very speculative possibility, probably not true at all, but it is an example of the surprises that could happen. Suppose our universe really is a surface, a three-dimensional surface in a higher dimensional bulk, is the physicist's word for it, a higher dimensional universe. And suppose that surface was formed, crinkled up like this crinkled sheet of paper. Then there is a tension in our surface, in our brain, a tension in the brain that will cause adjacent regions of this brain to, when they discover the existence of each other, the tension will cause the surface, our universe, to straighten out in the bulk. And as it straightens out, it vibrates and produces gravitational waves. So this is sort of a heuristic description of a process that probably doesn't occur, but it's conceivable that it occurs. And I just throw it out as an example. If you want to know what are the surprises going to be, here's a wild example of what a conceivable surprise would be. Okay, so I'll conclude just with the remark then that gravitational waves will be a major tool for astronomy, not just over the coming few decades, but into the next century and beyond. Thank you.
So Kip has very kindly agreed to answer one or two questions.
But the hour is late, and if everything was completely clear to everybody, then where'd this go?
I think people were so drawn up with everything you were saying. It was such a wonderful lecture that there's nothing else to say. So I think it's been a wonderful lecture.
Okay, thank you.
Brilliant tribute to Andy as well. Thank you so much for coming and speaking to us. Well, there is a question. Oh, well, there's a question. So let's have a
You know of any reason to have a LIGO detector in the southern hemisphere?
So a LIGO detector in the southern hemisphere, we would very much like to have a LIGO detector in the southern hemisphere. We hoped to have one put in Australia, but it required that the Australians come up with the cost of building the vacuum system facilities and the operating costs, which they could not see their way to doing because at the crucial time when we were negotiating with them about it, they were running a budget deficit for the first time in many years. And so the government said no after a lot of discussion, and then we went to India as our second choice. We had a full detector, all the components sitting in boxes, and it was a question of where were we going to assemble that. And Australia would have been the best place. India is a pretty good second choice. It's not as good as Australia would have been, but it's a pretty good second choice.
Yeah.
Thank you very much. This is a non-scientific question from a non-scientific member of the audience.
Wonderful.
I was fascinated not just by the theory of your talk, but also your insights into the practicalities of the LIGO experiment. You spoke very convincingly about the political will that made this possible. At a time when scientific funding is being squeezed in many countries, do you think there are any lessons to be learned from the successful funding of LIGO? How did you make it?
Well, I think it's a poster child for a successful payoff from a very high-risk project. We knew what the payoff would be if it succeeded. It truly is the analog of Galileo turning his telescope on the sky for the first time and opening up electromagnetic astronomy. So we knew, and that was part of the sales pitch, that the payoff would be huge. But the risk was very considerable, as I tried to convey. I think it is a tribute to a few people in government, the National Science Foundation, and a few people in the Senate, the U.S. Senate, that they understood in considerable measure what the payoff was and had some level of faith that the experimenters could pull it off. And that kind of courage in a funding agency, I'm told, at least in the US, is not nearly as likely to be seen, and maybe in Congress as well, as what we saw in the early 1990s. But I have no great lessons to learn, except here's an example, and that was what really was key. It was Richard Isaacson, who was program director for theoretical physics at NSF, and his boss, Marcel Bardon, who was the director of the physics division, who really pushed this through Washington. And they were full partners in this. And their names, I should have mentioned their names. Isaacson himself had been responsible for developing what was called the geometric optics approach to analyzing gravitational waves. Two length scale expansions, which he used to show that gravitational waves really do carry energy and to discuss conservation laws for energy and momentum for gravitational waves. So he was a very accomplished scientist, but also is superb at working the environment in Washington and making it happen. And that was crucial. It was crucial having Robbie Volk, but particularly Barry Barish, with the real skill to organize and manage this project, as I tried to emphasize. It was crucial to having the inventiveness and the vision of Ray Weiss, Ron Drever, and other experimenters around the world who also contributed in Glasgow and in Germany. All these things had to come together. It was crucial having superbly skilled people doing the numerical relativity in order to have the simulations that were needed when the waves were first detected. A large number of things had to come together to pull this off. And it's the poster child for success. When you pay attention to all of these things and you have the key people playing the key roles effectively.
Okay, one more question. Go ahead.
Yeah.
Thank you very much. I'm also a non-specialist. I did a maths degree a million years ago.
I did a physics degree a million years ago.
I've been waiting with excitement and impatience for the discovery since I read your beautiful and inspiring book, Black Holes and Time Warps, about 20 years ago. Can we look forward to a second edition?
I've been thinking about it, but I'll probably write a separate book. But I have several other projects I'm working on at the moment, and so that's sort of down a few years from now if I do it. But, I've sort of been there, done that, and my personal attitude is I want to do interesting new things. And I say one of the great pleasures of this was that I did succeed in training a younger generation of superb theorists who could play the role that I was playing in LIGO, and so I was able to get out without LIGO being damaged at all. And I did get out, and I am free to do other things, and I'm thoroughly enjoying doing other things and watching the superb team pull all of this off without me.
Perhaps we should have one last
Yeah,
question.
yeah.
Quasi-related comment and question. I was working on the superconducting super collider funding
Yes.
in Texas. I was part of that committee. And we couldn't keep that together. But I gather it was a lesser cost,
Yes.
fortunately, than what you're talking about.
Yeah, so this was the big difference, a huge difference. The SSC was at a level that it was a hot button issue on the floor of Congress. We were big enough that we were a hot button issue in committees, but never got to the floor of Congress. And so all we had to do was educate key members of, primarily of the relevant appropriations subcommittee that deals with NASA and NSF. And so we had it a lot easier. we also benefited enormously from the collapse of the SSC, because that's where we that's where we got Barry Barish. Barry Barish was the leader of there were two detectors in the SSC that were being built to detect the signals that were coming in. And Barry Barish was the leader of one of those detectors. And the SSC collapsed just a matter of months before we desperately needed his skills to carry LIGO forward. So.
Well, that's, of course, that might be the right note to end on. Let's thank Kip again.